In this problem, we're told that a gas and a piston cylinder assembly undergoes a cycle consisting of 3 processes. And this starts with a pressure 1 of 1 bar, a volume 1 of 1.5 cubic meters, and we're told information about the different processes. So process 1 to 2 is compression with the relationship PV is equal to C. Work 1 to 2 is equal to minus 104 kilojoules. Our internal energy at state 1 is equal to 512 kilojoules. And our internal energy at state 2 is equal to 690 kilojoules. Now we're told at process 2, work 2 to 3 is equal to 0 kilojoules. And our heat transfer 2 to 3 is equal to minus 150 kilojoules. Finally, we're told that process 3 to 1, our work 3 to 1 is equal to plus 50 kilojoules. Okay, so what are we trying to find? We are trying to find the heat transfer from state 1 to 2, the heat transfer from state 3 to 1, and our internal energy at state 3, and we're also asked, is this a power cycle? We're told that we can ignore the kinetic and potential effects, so that will simplify the problem a little bit. And as it turns out, some of this information is not necessary. We don't really care about in order to figure out what we're being asked, we don't really care the initial pressure, the initial volume. So to start out, let's start out with part A. And we're going to start with our energy balance. So our change in energy, and we're going to say from 1 to 2, is equal to the change of our heat from state 1 to 2. So this is the change of our heat transfer into the system minus the work, our system, the network out of the system. Now, what we can do is we can break up our change in energy like this. We can say our change of energy is equal to our change in kinetic energy from 1 to 2 plus our change in potential energy from 1 to 2 plus our change in internal energy from 1 to 2. And we know that the change in kinetic and change in potential energy are going to be 0 because we're told we can ignore these effects. So we can rewrite this down here. We can say a change of my internal energy from 1 to 2 is equal to Q 1 to 2 minus W 1 to 2. Last thing we can do to simplify this is we can say, all right, this change of U1 to 2 is really this U2 minus U1. And the order does matter. We're going from state 1 to state 2. So state 2 is our final state that we're at. State 1 is the initial state that we're at. So 2 minus 1 is our change in energy at this process. So then this is equal to Q, our heat transfer from 1 to 2, minus our work from 1 to 2. Now we're trying to solve for our heat transfer. So Q1 to 2 is equal to U2 minus U1 plus W1 to 2. All right, and I think we have all this. U2 is equal to 690, and everything's in kilojoules. So this is 690 kilojoules minus 512 kilojoules plus a minus 104 kilojoules. Now let's put that in our calculator, and we get that that is 690 minus 512 minus 104. So our heat transfer from process 1 to 2 is equal to plus 74 kilojoules. Okay, and now let's look at part B. And maybe you think, okay, this worked from 1 to 2. Let's try the same thing from 3 to 1. I know my bar is off and it says 2 to 3, but we're going 3 to 1. Okay, so let's do that. So the change in energy from 3 to 1 is equal to my heat transfer from 3 to 1 minus my work from 3 to 1. Okay? We can do the same simplification with my energy. So all I'm going to have is my change in internal energy from 3 to 1 is equal to Q, my heat transfer from process 3 to process 1, minus my work from process 3 to process 1. All right, and then finally, now this one, you have to think about it a little bit. We're starting at 3, we're going to 1. So it's going to be U1, that's my final, minus U3, which is my initial, is equal to Q 3 to 1 minus W 3 to 1. Okay, but now we're a little bit stuck, right? We know what U1 is. We know what my work is. We're trying to solve for my heat transfer, but we don't know what U3 is. And it turns out we're trying to look for U3 in part C. So this is probably not the correct approach that you would want to take. But we can use another piece of information that we know. We know that if we start at some state 1, we go to some state 2, we go to some state 3, and we come back to some state 1, well, we started at the same state that we stopped at. So this means that the change in energy of a cycle is equal to 0. So what I can say is my change in energy of a cycle is equal to the heat transfer of my cycle minus the work of my cycle. Well, this goes to 0, so I have the heat transfer of the cycle is equal to the work of the cycle. And what is the heat transfer and the work of the cycle? Well, I just add up all the different parts. So I'll have Q1 to 2 plus Q2 to 3 plus Q3 to 1 is equal to W1 to 2 plus W2 to 3 plus W3 to 1. And I know all these, right? 1 to 2, I found it's plus 74. 2 to 3, I know it's minus 150. It was given to me up here. 3 to 1, well, I'm solving for that. So I just have plus Q3 to 1 equals my work from 1 to 2. I know that. It was given to me. This was minus 104 kilojoules. Work 2 to 3. Okay, we were told this is 0 kilojoules. In work 3 to 1, we were told this is plus 50 kilojoules. So I can solve Q3 to 1 is equal to minus 104 plus 50 minus 74 plus 150. And we get that this is equal to plus 22 kilojoules. So this is part B. Well, now part C actually just comes right here, right? We're solving for U3. So U3 is really equal to U1 minus Q3 to 1 plus work 3 to 1. So we know what U1 is. This is 512 minus this 22 and then plus this 50. So my internal energy is equal to 540 kilojoules. So that's part C. Now, the last thing we're asked to do is we're asked to figure out, is this a power cycle? A power cycle requires that the work of the cycle be greater than 0. So we just have to add up these over here. So we'll have the work of the cycle is equal to work 1 to 2 plus work 2 to 3 plus work 3 to 1. All right, 1 to 2 is minus 104 plus 0 plus 50. Well, we can tell this is going to be negative, but just for completeness, we'll say that this is equal to minus 54 kilojoules. So no, it is not a power cycle, since the net work of the cycle is less than 0.